and air conditioning. Another important unit in the gate examination, which we could expect around definitely 5 marks, minimum 5 marks to 7 marks we could expect in this gate examination from this unit. First of all, what is meant by refrigeration? Refrigeration means maintaining a low temperature inside a confined space or volume with respect to the outside surroundings by spending some work or energy onto the system. Pictorially speaking, if you want to maintain, say for example, minus 10 degrees centigrade with respect to the hotter surroundings or environment or atmosphere, which may be say at 40 degrees centigrade. Inside this confined space, we would like to maintain minus 10 degrees centigrade as compared to the outside hotter environment of 40 degrees centigrade. How do we maintain this? Because of this temperature difference between the hotter surroundings and the confined space, heat will naturally transfer inside through the walls of the container. Because of the temperature difference, the heat would naturally flow. Whatever the heat that is flowing inside, if we can take it out by refrigeration cycle, by spending some work on the system, it is called refrigeration. A refrigerating cycle will extract or absorb from the low temperature and reject it to the environment or atmosphere, say at 40 degrees centigrade. So I can say the transfer of heat from low temperature to the high temperature by spending some work or energy input onto the system, it is called refrigeration. Refrigeration means maintaining a low temperature by extracting heat from it and rejecting it to the outside environment. According to the Clausius statement of second law of thermodynamics, whenever we want to transfer heat from low temperature to high temperature, some work has to be spent onto the system. Without this work input, we would never be able to transfer the heat from low temperature to the high temperature. This is meaning of refrigeration. What are the applications of the refrigeration? If you look at another perspective of the refrigeration, almost every house, in every house nowadays we are finding a refrigerator, household domestic refrigerator, in which we are maintaining the low temperature. For example, if this is a domestic refrigerator, inside which the average temperature say is minus 2 degrees centigrade, I suppose. The outside environment is at say 35 degrees centigrade. This low temperature is maintained by spending electrical power. Electric power is given to this motor plus compressor assembly. We doing work, and via condenser bank of tubes on the back side of the refrigerator, heat is rejected. This refrigerating cycle would extract heat from this low temperature and transfer it to the outside environment. This is a domestic refrigerator. So we are spending work, we are spending power onto the system. At the same time, we are able to maintain low temperature of -2 degrees centigrade as compared to the outside hotter environment of say 35 degrees centigrade. Any refrigeration system basically works on three principles. Number one, whenever a liquid changes its phase into vapor, it requires latent heat of vaporization for that change of phase. Whenever a liquid changes its phase from liquid phase to the vapor phase, it requires latent heat of vaporization. Number two, the pressure at which the change of phase from liquid to vapor occurs is known as saturation pressure. The pressure at which the change of phase occurs is known as the saturation pressure, and the respective temperature at which the change of phase occurs is known as saturation temperature. For example, water boils at 100 degrees centigrade corresponding to pressure of 101.3 kilopascal, that is say atmospheric pressure. Here for water, Psat is 101.3 kilopascal, Tsat is 100 degree centigrade. So for any pure substance like water, at a given Psat we have got only fixed Tsat. For any pure substance like water or maybe even refrigerant, at a given saturation pressure there is only one fixed value of respective saturation temperature. As the saturation pressure increases, the saturation temperature also increase. That means as the pressure on the water increases, say from 101 to 107, the water may be boiling at say 102 or 103 degrees centigrade. So as the saturation pressure increases, saturation temperature also would increase. That means water can be made to boil at any temperature we want by properly maintaining a superincumbent pressure on the water surface. Similarly, a refrigerant like CCl2F2 is boiling or evaporating, I can say, at minus 15 degrees centigrade at 1 bar pressure. Now the same refrigerant may be made to condense at 30 degrees centigrade by increasing the pressure of the refrigerant. That is the important point in any refrigeration system. A refrigerant, if it is say evaporating at minus 15 degrees centigrade at 1 bar pressure, now the same refrigerant may be made to condense say at 30 degrees centigrade by increasing the pressure of the refrigerant. The refrigerant vapor may be made to condense say at 30 degrees centigrade. That is the meaning of as the saturation pressure increases, saturation temperature also increases. That means here 1 bar pressure, the saturation temperature is minus 15. Say at 6 bar pressure, the saturation temperature may be 30 or 35 degrees centigrade for the same refrigerant. Now the third point, if you come to the third point, whenever heat is to be transferred from low temperature to high temperature, some work or energy has to be spent according to the Clausius statement of second law of thermodynamics. That is, whenever heat is to be transferred from low temperature to the high temperature, LT4 low temperature, some work must be given to the system. So based on these three principles, any refrigeration system do function. First point is, whenever a liquid is changing its phase into vapor, it requires latent heat of vaporization. Same latent heat will be released if the vapor is condensing back to the liquid. Second point is, the saturation pressure increases implies the saturation temperature also would increase. What do you mean by saturation temperature? Saturation temperature is the temperature at which the change of phase is happening from either liquid phase to vapor phase or from vapor phase to the liquid phase. So as the saturation pressure over the liquid is changing, respectively the saturation temperature also would change. The third point is, if you want to make the heat to transferred from low temperature to the high temperature, some work must have to be spent on the system. For example, if I take a refrigerant 12 in a container R12, which is a domestic refrigerant, and if the pressure is 1 atmosphere acting on it, that is open to atmosphere, that R12 would evaporate. They get converted into the vapor. This is liquid. If you keep a thermometer inside that, the thermometer will be recording, say, minus 15 degrees centigrade, the saturation temperature of R12 at 1 atmospheric pressure. Now, if you keep some closure over the surface of the R12, this is R12 liquid. I had a control valve. Now I have let out the vapor, refrigerant vapor. I have let out the refrigerant vapor at such a manner that the pressure acting on the refrigerant liquid is more than 1 atmosphere. Then if you keep the thermometer into the R12 liquid, if you assume, we watch that the temperature now would not be minus 15 degrees centigrade as the previous case. It may be, say, 1 degree centigrade. Now what we are seeing from these two figures, as the pressure over the surface of the refrigerant liquid is increasing, the saturation temperature is also increasing, as is seen by the thermometer. We could redraw the figure in a different fashion, how the saturation pressure and saturation temperature are interdependent. This is R12 liquid. Now I am just drying or sucking the refrigerant vapor. The moment it is formed over the liquid and the vapor is being drawn by the piston movement. This is piston. With the help of the piston, the vapor is drawn the moment it is formed over the surface of the liquid. Thereby, the pressure is maintained less than atmospheric pressure over the surface of the R12. Now, if you keep the thermometer, now the temperature may be even minus 30 degrees centigrade. So, by appropriately maintaining the pressure over the surface of the liquid, we could make the refrigerant R12 to evaporate at any temperature whatever we like to have. So, that is the dependence of Psat over the Tsat. So, the bottom line here is the saturation pressure, if it is manipulated, the saturation temperature also could accordingly be changed. Based on the above points or the facts, any refrigeration system could be designed. Basically, there are three types of refrigeration systems, namely, number 1, vapor compression refrigeration system, which is also known as mechanical refrigeration system. Number 2, vapor absorption refrigeration system. Number 3, air refrigeration system. Among all those three things, the first one is very important, that is vapor compression refrigeration system, which is also known as VCR. The cycle could be seen like this. The flow diagram of this system I am giving like this. The system basically has four components, namely evaporator, compressor, condenser, and then expansion valve. As the name suggests, in the evaporator, the refrigerant shall be evaporating from liquid phase to the vapor phase. In the compressor, the vapor is compressed, where we are spending our work. In the evaporator, the refrigerant absorbs heat. This heat is utilized as the latent heat of vaporization required for the change of phase of the refrigerant from liquid phase to the vapor phase. In the condenser, the refrigerant rejects heat because in the condenser, the condensation of the refrigerant vapor occurs, wherein the change of phase occurs. Hence, the latent heat of condensation will be liberated, which will be given to the surrounding ambient atmosphere. Now, let us draw the flow diagram once again. It is a constant pressure evaporation of the refrigerant. As the refrigerant is passing through the coil of evaporator, it evaporates at constant pressure and also at constant temperature. The state of the vapor leaving the evaporator is dry saturated vapor. That is the state of the refrigerant leaving the evaporator. A motor does work required for the compression of the refrigerant vapor from evaporator pressure to the condenser pressure. This is the pressure at evaporator, it enters, and pressure at condenser, the refrigerant leaves. In the condenser, the refrigerant rejects heat. The superheated vapor refrigerant leaves. The refrigerant rejects heat in the condenser. By the time it leaves the condenser, it should be the saturated liquid at condenser pressure. This saturated liquid expands from condenser pressure to the evaporator pressure when it passes via throttling device. So the state of the refrigerant leaving the throttling device is wet mixture. If you represent the cycle on temperature entropy diagram, the VCR cycle. This is also called simple dry saturated VCR cycle, vapor compression refrigeration cycle. This is entropy state 1. This is state 1. This is evaporation. This is Tsat at the evaporating pressure. The state of the refrigerant leaving the evaporator is dry saturated vapor, as I had mentioned earlier. 1 to 2. This is 2, state 2. This is isoentropic compression. 2-3 is the desuperheating and condensation. This is a Q rejected, this is Q absorbed. 3 to 4 is expansion. Where enthalpy remains constant. 2-3 is cooling with the condensation. Q rejection here. So totally there are 4 processes involved in the cycle: evaporation, compression, where work is required, condensation, and expansion. So this is called simple dry saturated vapor compression refrigeration cycle. Now let me explain about the cycle. Process 4-1 is isobaric and isothermal evaporation of refrigerant liquid in evaporator, wherein the refrigerant absorbs heat from the surroundings of evaporator, producing refrigeration effect or cooling effect. Next, process 1-2 is isoentropic compression of refrigerant vapor from evaporator pressure to condenser pressure, during which the refrigerant vapor becomes superheated. Process 2-3 is isobaric first cooling or desuperheating, and then condensation of refrigerant vapor, during which heat is rejected by refrigerant to the coolant circulated around the condenser bank of tubes. In domestic refrigerator, the coolant is atmospheric air circulated around condenser on the back side of the refrigerator. Usually a natural convection. By natural convection, heat transfer occurs. The state of the refrigerant leaving condenser is saturated liquid at condenser pressure. That is state 3. Process 3 to 4 is expansion or throttling of refrigerant liquid from condenser pressure to evaporator pressure. During which a small fraction of liquid refrigerant evaporates into vapor. Hence, the state of refrigerant leaving throttling valve or entering evaporator is a very wet vapor. Let us indicate simple dry saturated VCR cycle on pressure enthalpy diagram. This is very important diagram. We could understand the cycle on pressure enthalpy chart. (4-to-1) is isobaric, Q-absorbed in evaporator and as well as isothermal. Temperature is also constant. 1-to-2 is isoentropic compression from evaporator pressure to condenser pressure. The state 2 is a superheated vapor. 2-to-2, this is cooling. 2-to-2, I'm sorry. 2-to-2 is cooling of refrigerant. Where? In the condenser. At 2-to-3 is condensation at saturation temperature corresponding at condenser pressure. This is saturated liquid, the state of the refrigerant leaving the condenser, which expands at a constant enthalpy in the throttling valve or expansion device. So this is the pH chart. During 2-to-3 temperature remains constant. During 4-to-1 temperature remains constant. What is 4-to-1? T4 is equal to T1 is Tsat at evaporator pressure. T2 is equal to T3 is equal to saturation temperature of refrigerant at condenser pressure. Now let us define refrigeration effect, RE. It is the amount of heat absorbed by 1 kg of refrigerant while passing through the evaporator from the surroundings of evaporator. Evaporator is a heat exchanger in which the refrigerant is absorbing heat. It is entering at enthalpy H4 and leaving at enthalpy H1. It is absorbing heat from the surroundings of the evaporator at a constant pressure. Therefore, refrigeration effect is equal to Q absorbed at constant pressure, which is nothing but H1 minus H4 kilojoule per kg. H1 is Hg at evaporator pressure of refrigerant, which is to be taken from the refrigerant tables. Now, work done. Into the compressor, refrigerant is entering at an enthalpy of H1 and leaving at an enthalpy of H2. Compressor is driven by the motor. S is constant. It is isoentropic compression. S1 is S2. Using the TDS relation, TDS is equal to dH minus VdP. When S is constant, ds is 0, implies dH is equal to VdP. Integral dH is integral VdP. But integral VdP is the work done on the refrigerant by compressor for raising its pressure from evaporator pressure to condenser pressure. Therefore, work done in compressor per kg is equal to H2 minus H1 kilojoule per kg. Now let us define coefficient of performance, abbreviated as COP. It is defined as the ratio between refrigeration effect and work done. H1 minus H4 divided by H2 minus H1. But during throttling, enthalpy remains constant. 3 to 4 is throttling, implies H3 is H4. Therefore, COP of refrigerating cycle is H1 minus H3 divided by H2 minus H1. This COP is usually greater than 1, but it is not compulsorily should be greater than 1. Usually for domestic refrigerators, COP will be obtaining around 2.5, 3 in that range. Here H3 is HF at condenser pressure of refrigerant from tables of refrigerant, because state 3 is a saturated liquid state. So H1, H3 could be obtained directly from the table, whereas H2 is enthalpy of the superheated refrigerant at condenser pressure and superheat temperature T2. Now let us define ton of refrigeration. Ton is the unit of refrigeration capacity. It is defined like this. If the refrigerant absorbs 50 kilocalories of heat in 1 minute from the surroundings of evaporator while passing through it, then the capacity of plant is said to be 1 ton. The tonnage capacity is usually mentioned in tons. For example, if the refrigerant is passing through the evaporator and absorbing 50 kilocalories in minute, then the capacity of this system is said to be 1 ton. 1 ton is equal to 50 kilocalories per minute multiplied with 4.2, we get in kilojoules, because 1 kilocalorie is 4.2 kilojoules. 210 kilojoules per minute, that is 3.5 kilowatts, that is also can be called as 3000 kilocalories per hour. Any one of these things could be used for calculating tonnage. Most prominent is 210 kilojoules per minute. Now let us see the formula for tonnage capacity of refrigeration system. If m dot Rf is the mass flow rate of the refrigerant passing through the evaporator, then H4 is the enthalpy of the refrigerant entering the evaporator, H1 is the enthalpy leaving evaporator, enthalpy of refrigerant leaving evaporator, and H4 is entry enthalpy. Then refrigeration capacity in tons of the system is mass flow rate of the refrigerant into H1 minus H4 divided by 210 tons, where H1 and H4 are in kilojoule per kg. Now let us see how to calculate the work done per second or power of compressor. Power is equal to work done per second in compressor, that can be written as mass flow rate of the refrigerant into work done per kg of refrigerant, that is mass flow rate of the refrigerant into H2 minus H1, so many kilojoule per second. In the here, this is mass flow rate of the refrigerant is in kg per minute. M dot means mass flow rate. But how to calculate the H2? Because H2 is the state of the refrigerant in the superheated domain, in the superheated region. To get H2, we need T2 because H2 is equal to H2 dash plus Cp of the refrigerant vapor into T2 minus T2 dash. T2 dash is a saturation temperature at condenser pressure. But how to get T2? To get T2, S1 is equal to S2. What is S1? Sg at evaporator pressure is equal to S2 dash plus Cp of the vapor into log ln T2 by T2 dash. What is S2 dash? Sg at state 2 is a dry saturated vapor state at condenser pressure plus Cp is the specific heat of the vapor at constant pressure ln T2 by T2 dash. T2 dash is equal to Tsat at condenser pressure. So from this equation, evaporator pressure, from this equation we can calculate temperature in Kelvin, temperature of the refrigerant after compression. Please note that T2 and while writing the logarithmic ratio, the T2 and T2 dash, both the temperatures must be in Kelvin scale. T2 is the superheat temperature at condenser pressure of refrigerant, that is at the end of the compression. Once we know the T2, immediately we can calculate H2, that is enthalpy of the refrigerant after the isoentropy compression. Then we can obtain COP and as well as the work done per second in the compressor also. Now let us see subcooling in vapor compression, refrigeration cycle. Now I shall draw the subcooling on the temperature entropy diagram. This is evaporation at constant temperature. This is compression, isoentropy compression from evaporator pressure to the condenser pressure. This is cooling. This is condensation of the refrigerant vapor at constant condenser pressure. State 1, state 2, state 2 dash 3. 3 is a saturated liquid. In the previous simple VCR cycle, we have seen that at state 3, the refrigerant is entering the throttling device or expansion device. Now, in this case, this liquid is further cooled, subcooled within the condenser to state to 4 and then allowed to expand in the throttle valve. So this 3 to 4 is subcooling in the VCR cycle. So I can say 1, 2, 3, 5 dash is simple dry saturated VCR cycle as we had discussed earlier. 1, 2, 3, 4, 5 is subcooled cycle. So I define subcooling like this. Subcooling means cooling the liquid refrigerant below its saturation temperature corresponding to condenser pressure within the condenser. Now the subcooled cycle on pH plane also we can indicate. This is simple dry saturated. This is subcooled. 1, 2, 2 dash, 3, 4, 5. This is 5 dash. This is subcooling done in the liquid zone. 3 to 4 is subcooling. 4 to 5 is expansion or throttling, where enthalpy remains constant. This is the representation of the subcooled cycle on pressure enthalpy diagram or pH plane. This is isoentropic compression. 1 to 2, 2 to 2 dash is cooling, 2 dash to 3 is condensation, 3 to 4 is subcooling, 4 to 5 is expansion via throttle valve. Now let us see effects of subcooling. Number 1, as we have seen from the figure, the liquid mass of refrigerant entering evaporator increases in the mixture. The liquid mass of refrigerant in mixture or wet vapor entering evaporator increases due to subcooling. That is, X5, that is dryness fraction of refrigerant. X is dryness fraction, where X is dryness fraction of refrigerant. Naturally, when there is more liquid available at the entry to the evaporator, the refrigerant can pick up more heat from the surroundings of the evaporator. Therefore, refrigeration effect increases due to subcooling. By what amount? It increases by H5 dash minus H5. By this much amount we get an extra RE. This is extra RE we get by providing subcooling in the cycle. Number 3, work done per kg of refrigerant remains the same, since 1 and 2 state 1, since states 1 and 2 are not changed, because work done is H2 minus H1, work done per kg of refrigerant would not change.